Now what we're going to be doing in this unit is we're going to actually get into the actual intention of this outcome where we talk about logarithms, where we're going to talk about evaluating, relating logarithms to exponents, deriving the laws of the logarithms, solving equations, and graphing. Now in section 1, we're going to be talking about actually these 3 points where we're going to evaluate, relate, and solve some equations. Section 2 and 3, we're going to talk about the graphing, and section 4, we're going to talk about the laws. That's all of our outcome, which is a lot, but we've already kind of hit a lot of stuff with the exponentials. Here's our intentions, talk about the graphing, talk about the equations, which leads us into actually understanding logarithms. So for the exponential function, y equals c to the power of x, which is the base form for an exponential, the inverse would be x equals c to the power of y, where literally the x and y are just switched, because that's how we deal with inverses. We switch in the x and y. Now where this takes it further is this inverse is also a function that's called a logarithmic function. But since we deal with switching these x and y's, we also talk about how do we solve this equation to get the y by itself. What mathematicians have come up with is this idea of dealing with a logarithm, where it's y equals log base c of x, where c is a positive number other than 1, and hopefully I'll make a mention of why it's other than 1, but you'll see in a second. But what I call this is the Whiplash method. So if we deal with like some shoulders and a neck, head, the idea behind a whiplash is obviously if you're dealing with a front and back, if you get rear-ended, there's your headrest, which stops your head from actually snapping back and possibly breaking any tendons. But if you were to be struck from the side, what will happen is that your head will move. Now, hopefully it doesn't actually detach, but it's going to move from one side back to the other before trying and stabilize itself. And that's the entire idea behind whiplash. It's just boom, just big switch. Where that, what I call this whiplash is if we're dealing with the logarithmic form, in order to get to the exponential form, all that we do is we start with this base, switch it over to the y. So you start with your c to the power of y will equal x. And that is the idea behind whiplash. We go from one side to the other and back. One side to the other and back. Again, hopefully your head doesn't actually detach like that, because that would be less than desirable. Now, one little note is that since our number system is based on powers of 10, logarithms with base 10 are widely used and called common logarithms. When you write a common logarithm, you don't actually need to write the base. For example, log 3 actually means log base 10 of 3. So let's get into some examples that really help illustrate this. If we're going to quickly evaluate this equation, log base 7 of 49 equals x, what we do is we start with the 7, go over to the other side, 7 to the power of x equals 49. Again, that's the idea of starting with one side, going to the other, and back. We started with our base, 7, went over to the other side, 7 to the power of x equals 49. So in this case, we have to say, okay, 7 to the power of x equals 49. Well, we know something. We know that 49 is 7 to the power of 2. It's 7 squared. So x equals 2, and we're done. It is literally as simple as that. So even if we got to an equation like this, x equals log base 6 of 1, we start at our base, we go over to the other side. So 6 to the power of x equals, and that would equal this big number, this large number, 1. That would equal 1. That actually looked like an arrow. 6 to the power of x equals 1. Well, 6 to the power of what gives you 1? Remembering that 1 is actually any number to the power of 0. So x equals 0. If we got into these kind of questions, just a nice little reminder again, the common logarithm always has a base 10. So this question could actually be rewritten as x equals log base 10. Oh, it's not letting me write the 0. There we go. Of 0. Oh wow, that's not fun. Of 0.001. So let's use our whiplash. 10 to the power of x equals 0.001. This is just getting bad. Okay. Now we have to say 10 to the power of what gives us 0.001. Well, we know that 10 to the power of 1 gives us 10. 10 to the power of 2 gives us 100. So how do we get a small number? Well, it's the idea of getting down to very small numbers. And this one makes actually a lot of sense in this context, because this is tenths, hundredths, thousandths. So this is 1,000th. This will actually let me draw zeros now. There we go. Okay, but 1 over 1,000, 1,000. Now I'm going really long and convoluted explanation to this, so I just gotta move everything down a little more. 1,000 is 10 to the power of 3. So if I want to rewrite this, this would be 10 to the power of x. And to rewrite this, because it's in our denominator, to put it to our numerator so we actually have an actual base of 10, it would be 10 to the power of negative 3. Which means x equals negative 3. If we do this one, 2 to the power of x equals the square root of 8. If it will let me draw an 8 now. There we go. But we know that 8 is 2 cubed. Oh my goodness. Make this look like a 3. And square root. Well, square root, if we want to rewrite it, I'm just going to kind of combine 2 steps in one. The notch goes into denominator. So that'd be 3 to the power of 1/2. Sorry, 2 to the power of 3 to the power of 1/2. Which means we actually have 2 to the power of x. Exponent with an exponent, we multiply those exponents. It'd be a 3 over 2, because 3 is the same as 3 over 1. And when you have a power with a power, you multiply exponents. So 3 times 1, 1 times 2. X equals 3 over 2. So I did allude to this idea. Oh, a little bit higher. We can't really have that base, that c value being 1, because it's just going to be redundant. Same time, it's just not going to work. Because if this was base 1, so log base 1 of something would have to equal, say, if you say x, 1 to the power of anything is just going to be 1. So literally what this is saying, this little line here is saying, So the log base 1, I'm just going to leave this space blank for a second, of x, well, 1 to the power of what gives you what? 1 to the power of anything will just give you 1. So it's just kind of a redundancy. X could actually be anything, which means you actually have an infinite amount of answers. So that's why I had to put this little stipulation in there. Okay. Let's go into more complex stuff. Base is 5 to the power of -3. That looked like a -3 equals x. Okay. Well, we don't have to solve for an x. We have to just evaluate what is 5 to the power of -3. The negative exponent means we're going to take the reciprocal of it. And 5 to the power of 3 is 125. So 1 over 125 is x. That's all there is to it. If we go here, this one's going to be a little bit different, but it's going to be really nice. X to the power of 2. So we keep on using our whiplash no matter what. X to the power of 2 equals 36. So what number squared gives us 36? 6. Of course, if you want to show your work for this, it's just really nice and easy. Take the square root. Now we do have to take the principal square root, which does mean that we're only dealing with the positives because of this extra little stipulation, where the C value, it always has to be a positive number. So a positive number does mean that we can have a decimal, but we just can't have 1, and we definitely can't have negative. Even though -6 absolutely, -6 squared absolutely is 36, this number can't be negative. It just can't. If we do our whiplash here, 64 to the power of 1/2. My rating is actually going to show up. Equals x. Well, 1/2 just means, wow, that is supposed to be a 4. Make it a 4. What is the square root of 64? X equals 8. And there we go. We do have a few more things on the back. In math, we also have what's known as the natural logarithm. Now, what I really should do is I should bold that. Now, since the common logarithm has base 10, the natural logarithm actually has the base e, where e is known as limit as n approaches infinity of 1 plus 1 over n to the power of n. Now, this is just some fancy calculus speak. Long story short, this is actually a number that is already programmed into your calculator. Now, depending on which type of calculator you have, it's in there. On the Texas Instruments, the X2S, it is found right on that LN button. So you access it by pressing the second and then you press the second and then you press the ln button. Now that's actually notated by this. Ln x is the same as log base e of x. And the way that you pronounce it is just like grass. Ln. Kind of weird, but that's what it is. So let's get into some stuff. Now, just a little note, this E is not the capital EE that you will see on that x to the power of -1 button. That's your scientific notation button. That's not that, it's on this ln. So if we want to evaluate these logarithms, log base 2 of 5x plus 7 equals 5, we're going to use our whiplash. 2 to the power of 5 equals, make this actually right, 5x plus 7. Before we get there, 2 to the power 5 is 32. What the heck? Okay, 32. And I just need to write a little bit slower to make it retrieve my stuff. So 2 to the power 5 is 35, or sorry, 32 equals 5x plus 7. Well, how do we solve? We subtract the 7. 25 equals 5x. Sorry, I have to make that look a little bit nicer. And then to solve for the x, we divide by the 5. So x equals 5. Now for right now, don't worry about checking yourself. Obviously, this stuff will be really easy, but I'm talking about plugging it back in here. Log base 2 of what gives you 5? Well, actually, this one is something that's nice to do. Never mind. Log base 2 of, well, what's 5 times 5 plus 7? 5 times 5 is 25. Plus 7 is 32. Is that true? 2 to the power 5 equals 32? Yeah. So that one actually works. Okay, here's what I was talking about before. Ln of 4x plus 1 equals 3. Well, again, all that we're really worried about is that ln is a log base e. Really, we can just say that's log base e. So if we use our Pythagorean, or sorry, not, yeah, we use our Whiplash, e to the power of 3. Okay. Pen is just not being nice to me. Maybe I just need to write a little bit harder. There we go. E to the power of 3 equals 4x plus 1. So if I'm going to evaluate this, I'm going to put e to the power of 3 in. So I'm going to press second ln, and it automatically puts that power. So I already have on my calculator, it already says e to the power of something. So in this case, all I have to do is put 3. And it's 20.08553692. Now I'm just going to leave that on my calculator because we're going to quickly manipulate. If you erase this and go and round it beforehand, please go at least 4 decimal places, but because these are really nice and simple, just leave in your calculator. Please. Add the 1, obviously this would just be a 21.0855, blah, blah, blah. Equals 4x, divide by the 4, and x would equal, I'll go 2 decimal places, 5.27. So if we wanted to check, this one is actually something that we could actually type into your calculator because it automatically will do it. If we actually type in the ln of 4 times 5.27, of course, keep in mind that this is a rounded value, minus 1. If you type that into your calculator, so instead of pressing the second ln, you just press ln of 4 times 5.27 minus 1. I get 2.999724295, but again, because that's rounded, it's effectively 3. You don't have to check your stuff, but it doesn't hurt. Let's keep on going. E to the power of 4. Sorry, not e. 3 to the power of 4. 7x minus 3. 3 to the power of 4 is 81. 7x minus 3. So I add the 3. 84 is 7x, divide by the 7. X should come out as 12. Just have to type that in my calculator, just double check. All right. Okay, so last time, I know that systematic trial and error is not your favorite, but it's useful in some cases. I will show you a way of doing this faster, and you will very likely like it a lot better. We have to try and estimate log base 2 of 14. You can't actually type that into a calculator yet. There is a way to do it, but all that we're doing is saying it equals x, equals y, equals something. So let's try and evaluate to 2 decimal places. 2 to the power of x equals 14. So since we already know that, let's see, 2 to the power of 5 is 32. 2 to the power of 6 would be 64. Just kind of side note, 2 to the power of 6 should be 64. I'm doing that right. Yeah. And 2 to the power of 7 should be 128. Obviously, it would have to be 6 point something. So since, oh, wow, sorry. Ignore that. 14, not, for some reason, I was thinking 100 over here. I'm sorry, guys. 2 to the power of 3 is 8. 2 to the power of 4 is 16. Here we go. That's going to be a lot nicer. Okay, so it have to be 3 point something. So obviously it's going to have to be on the higher end of 3. Let's try 3.7. So 2 to the power of 3.7. I get 12.99. Okay, not good enough. 3 to the power, or 2 to the power of 3.8. 13.4288. Okay, not close enough. If you go to 3.9, it's 14.92, which is too far. So 2 to the power of 3.8 is, sorry, not 12, 13. 0.92, and 2 to the power of 3.9 is 14.92. So it'd have to be somewhere between 3.8 and 3.9. Let's see, I'm going to go on the lower end because I want to be as close to 14 as possible. So 2 to the power of 3.82. Let's try it. Okay, that's 14.1. 81, 14.02. So if I just go to 2 decimal places, the closest that I could probably get would be that 3.81. I get that 14.02569, which is probably as close as we're going to get. So our answer is 3.81. Of course, we could go further, we could get more decimal places, but if I just ask for 2 decimal places, we're good. Just for reference, the full answer to about 9 decimal places is 3.807354922. And I will show you how you can get that later. All right. Last of this trial and error, or sorry, not last one, but another one. 3 power of what gives us 100? So I know that 3 power of 3 is 27. 3 to the power of 4 is 81. 3 to the power of 5 should be 243. Just double check that. Yep, 243. So obviously it's going to have to be somewhere on the lower end of 4. 3 to the power of 4 point something. So if I go 3 to the power of 4.3, I'm at 113 almost. 4.2. on 100.9. So obviously it's going to have to be 4.1 and 4.2. You don't necessarily have to do this. A lot of it's, all of your work is by trial and error. I'm perfectly fine with you putting this straight into your calculator and trying to estimate as best as you can. I'm just kind of writing it down just for, so you know where my brain is thinking. 100.9, 4.1 is 90.4. So this would have to be obviously on the higher end of 4.1. So if I go to 4.9, or sorry, 3 to the power of 4.18. 18 is 98.7. 19, 99.8. So 3 to the power of 4.19 is 99.801727, which is as close as we're going to get with 2 decimal places. Just for reference, 2 9 decimal places, it will be 4.191806549. But for 2 decimal places, 4.19, perfect. And some last examples. In 1935, American seismologist Charles R. Richter developed a scale formula for measuring the magnitude of earthquakes. The Richter magnitude m of an earthquake is defined by m equaling log of a to the power of, or a over AO, where A is the amplitude of the ground motion, usually in microns, measured by a sensitive seismometer, and AO is the amplitude corrected for the earth distance to the actual earthquake that would be expected for a standard earthquake. The strongest recorded earthquake in Canada struck Haida Gwaii off the coast of British Columbia in 1949. It had a Richter reading of 8.1. How many times as great as AO was its amplitude? So this one's actually, it's again, it's a word problem to try and see the context of it. We're going to go really quickly. Richter magnitude m is 8.1. Log of A over AO. So to find out how many times it was, log is the same as log base 10, which means if we do our whiplash, 10 to the power of 8.1 would equal A over AO. So how many times is great? If we just quickly manipulate this equation, multiply both sides by the AO, the amplitude will be 10 to the power of 8.1 AOs. If you type that in your calculator, 10 to the power of 8.1 is 125,892,541.2 times as big. Now, largest measured earthquake struck in Chile in 1960. It measured a 9.5 on the Richter scale. How many times greater was it than the Haida Gwaii? Well, using the exact same kind of bit, this earthquake is 10 to the power of 8.1. So this one would be a 10 to the power of 9.5 AOs. If we want to find out how many times greater it is, really all it is just dividing both sides by, or dividing this one by a 10 to the power of 8.1 AO. And I don't put a lot of word problems into these because it's really more contextual, just to see where this is actually applied. So if you're going to some kind of engineering or thing or into some more scientific base, that's where we're getting this application. Just like you might have actually seen logarithms. If you have already taken chemistry, or if you're going to take chemistry, you're going to see some logarithms. Long story short, AOs cancel off, and if we have 10 to the power of 9.5 and 10 to the power of 8.1, if you have the same base and you're dividing, you should subtract those exponents. So 9.5 Subtracting that 8.1 is 1.4. And 10 to the power of 1.4 is 25.1 times. Actually, sometimes I don't like writing it. It's 25.1 times as big. So just because it had a Richter scale reading of 1.4 times bigger, it was actually 25 times stronger. And as that will be evident in the Richter scale reading that I actually put on your page as well. That kind of Richter scale from 0 to 1 is about same as 0.6 to 20 kilograms of dynamite, which really we can't feel. You really can't start feeling anything until a 3, but even you have to really be very close to it to feel. 4, you're going to start actually feeling. Whereas when we start getting into 6s, can cause great damage, but usually right around where, right above where it happens. 7 can be detected all over the world. It can actually cause some serious damage. But as soon as we get to a 9, it's very rare, and it does cause unbelievable damage. So a 9.5 is something that is intense. And I know that one thing that whenever I teach Science 7, I do make the connection that every single step, which is why it's dealing with the logarithm, every single step, wow, make this an actual arrow. Every single time it goes up a scale, it makes it 10 times stronger. So a 7 is 10 times stronger than a 6. A 5 would be 100 times stronger than a 3. So again, there's the application to logarithms. And some fun fact already. And now you can have some fun.